Hi guys, welcome to the today's session of design and analysis of algorithms. In this session, we are going to see one more application of transform and conquer algorithm design strategy, which are nothing but balanced search trees, right? So here we are going to explain about what is a balanced search tree. So here we are going to discuss about two balanced search trees. One is AVL trees and other one is 2-3 trees, right? So first of all, what is a balanced search tree, right? A balanced binary tree is a balanced binary search tree is a binary search tree in which the depth of two subtrees of a very node never differs by more than one. That is the depth of two children, right? Suppose, for example, if you are taking a binary search tree like this, so here, if you are taking a binary search tree like this, okay. Now, if I find the depth of the tree at every node, if I find the depth of the tree at every node, so at any node, the depth of the tree should not differ by more than one, okay, of its right and left subtrees. Now I see the depth of this one, and the depth of this becomes this minus this, so which should not be more than one, right? So this is to be called as a balanced search tree. So this tree is also to be called as height balancing tree. Here we are balancing the height. We are finding the depth of the tree, means it is nothing but the height of the tree. Height balancing. We are doing whether the tree is height balanced or not, right? So this property ensures that the tree remains balanced, and which can lead to efficient operations such as insertion, deletion, searching, and all these operations can be done efficiently if the tree is balanced, right? So that's why we are using this balanced binary search trees. Now, two types of balanced binary search trees are there. So here you can see instance simplification variety and the representation change variety. So you already seen the variations of transform and conquer, right? The three types of variations that you see. One type we already explained, right? These two types, instance simplification and representation change. Those two things that we are going to explain now. Now, instance simplification variety means an unbalanced binary search tree is transformed into a balanced one. Here, we are given an unbalanced binary search tree. This unbalanced binary search tree is transformed into a balanced one. So, because of this, those trees are to be called as self-balancing trees. And the example for that self-balancing trees are AVL trees, red block trees, right? And coming to the representation change variety, so this variety of trees allows more than one element in a node of the search tree. They allows to more than one element in a node of search tree. And in a node, generally we will represent one element. Suppose, for example, if this is a node, here I will represent one element. Here, this is a node, here I will represent one element. If this is a node, here I will represent one element, right? But in case of this representation change variety trees, it allows the presence of more than one element in a node, right? So the examples for this representation change variety of trees are 2-3 trees, 2-3, 4 trees, B trees, etc. Right. Now we are going to see the AVL trees and the 2-3 trees as examples for each of these varieties of balanced binary search trees. So first we are going to see AVL trees, right? What is an AVL tree? An AVL tree is a binary search tree in which the balancing factor is either 0 or +1 or -1. So here what is meant by balancing factor? The difference between the heights of nodes left subtree and nodes right subtree, right? Here you can see, here I given two examples. This is one example and this is other example. Here this becomes a AVL tree, but this is not an AVL tree. Let us see why it is not becoming AVL tree, why this is becoming a AVL tree. Now, and what is height balancing or balancing factor here, right? Now let us see. So here I have node 2. This doesn't have any left nodes or right nodes, right? So its balancing factor is 0, right? Here, if I see this one, this is having one left child, no right child, right? So its balancing factor is 1 minus 0, which is nothing but 1, right? Coming to this node, here also there are no left childs and right childs, so balancing factor is 0. And coming to here, this is having one right child, but there is no left child. So that's why 0 minus 1, which becomes minus 1. Its balancing factor is minus 1. And here, here I can see it is having one left child and one right child. And in every of these left childs and right childs, there are two nodes are present. So that's why it becomes 0 only. The balancing factor is 0 only. So at any node, the balancing factor is 0 or 1 or minus 1 in this tree. And also, this is a binary search tree. What is the property of binary search tree? It should be a binary tree. That is, at most it should have, every node should have at most 2 childs. And binary search tree means the key elements always should be present in such a way that the left subtree should have the less values when compared to that of the parent. Right subtree should have the more values when compared to that of the parent. Right, here you can see the left subtree whose value is 3, which is less than 5. Right subtree whose value is 6, which is greater than. And left subtree, which is less than its parent. Right subtree, which is greater than its parent. So all the elements which are present in right subtree are greater than the root node. All the elements which are present in the left subtree are less than the parent. Right, so that's why we can call it as a AVL tree. It is a binary tree, it is a binary search tree, and its balancing factor is either 0 or plus 1 or minus 1. That's why it should be called as an AVL tree. But coming to here all the nodes are having a balancing factor 0. But it is not an AVL tree because it is not a binary search tree. So here you can see here this right subtree is having higher value. Right, here left subtree is having higher value. Lower value. Right subtree is having lower value. Left subtree is having higher value. So it is not a AVL tree. Right. So I hope that you all understood why this becomes AVL tree and why this not becomes AVL tree. Right. Now coming to AVL tree rotations, we have mainly 4 types of rotations in AVL tree. These rotations are used to transform the subtree rooted at a node and to balancing factor become either plus 2 or minus 2. Okay. In order to make it as height balanced, we are using different rotations. So what are the 4 types of rotations that we have are single R rotation, single L rotation, double LR rotation, double RL rotation. Right. R means right, L means left. Right. We are going to see each and every type of rotation here. Now let us see single R rotation. So in this case, we are going to rotate the tree into the right direction. Right. So here you can see, R is the root, C is the child. How it is to be rotated? C becomes the parent and R becomes the child. So always, since it is a binary search tree, here this value is greater. So when I want to rotate it, definitely when it becomes root, definitely it should be the right child. So that's why it comes to the right part. And here you can see, definitely this is a greater value. It should be the right value. And for this, you can see this is a greater value, this is a less value, and this is the greater value. When it becomes the root node, in that case, the greater value should not be present in the left child. So that's why T1 presents in the left child and T2 comes to the left of R, right? Like that, it will be rotated. Now here you can see one example, 1, 2, 5, right? Now here in this 1, 2, 5, if I do the R rotation, my 2 becomes the root node. And this is since less than 2, it becomes the left child, and this is greater than 2, this becomes the right child. Now here, if you see this one, in my left child, I have 2 children, In my right, I didn't have any children, so its factor is 0. So that's why its balancing factor becomes 2. Now I want to make it as a height balance. So that's why I'm doing R rotation, right? So by doing R rotation, the balancing factor of every node becomes 0, right? So that's why for doing the tree as height balanced, I need to use these rotations. Now you can see the next rotation, L rotation, single L rotation. So here you can see R is root and C is the child. If I do the L rotation, C becomes the parent, R becomes the child. Now you know that in a binary search tree, R is always a less value when compared to its right child. So always R is the less value. So when I rotated this, C becomes the parent. Since R is less value, it comes to the left child, right? And here T1 is left child of R. So since its left child is having less than it, it also becomes, here also it becomes the left child. But coming to here, T2 is less than this C and T3 is greater than this C. When C is root, this T3 becomes the right child, but I cannot represent a less value of C in the right child. So that's why this 2 becomes the right child of R, right? Like this, it will be rotated. Now here you can see, here I have how many children in the right side? 2 children in the right side, but left side there are no any children. So here what is the balancing factor? 0 minus 2, which becomes minus 2. So here I didn't have minus 2 for the height balance tree. It now becomes AVL tree. So for that I am going to apply the rotation. When I did L rotation, my 2 becomes the parent, then 1 becomes the child, left child, and 3 becomes the right child, right? So this is to be called as L rotation, right? Next we are going to see next double LR rotation, left rotation and right rotation, right? So in this case, first we are going to apply left rotation and then we are going to apply right rotation. So finally, how you will get is like this, height balanced, right? So initially, this is the root, this is the left child. For this left, this is the right child, and this is the right child for R, this is the left child for C, and this is left child for G and right child for G. So when I apply LR rotation, it should be represented as like this. Now my G becomes root node. Since C is less than G, this becomes its left child, and R is definitely it should be greater than G, so it becomes the right child. And here you can see T1 is left child of C, which is present as usual, but here for G, T2 and T3 are present. My T2 comes to the right child of C, and my T3 comes left child of R. Right. Now here you can see. So here let us see. This is C, this is R, and this is G. Let us see how G is. G is 2, right? Where my C is present, C is here, and my R is present here. Like that, it is to be transformed. First, I will do L rotation, then I will do R rotation. When I did the L rotation of this one, this is to be represented as like this. When I did the R rotation, then it comes to these rotations. Right. Now, I hope that you understood this LR rotation. Next, we will see RL rotation. Double RL rotation. Now, here you can see this is the R, this is C, and this is G. This is the left child, this is the right child of C, and this is left child of G and right child of G. Now, when I apply RL, that is first we apply right rotation and then we apply left rotation, right? Now, this G becomes, when I apply first right rotation, this G becomes, when I applied RL rotation, this G becomes the root node, and R, always R, since it is the right child, always R is less than G, so that's why R comes to the left child and C comes to the right child. Now, in this case, let us see, my T1 is the child of R, so obviously it is present here only. My T4 is the right child of C, obviously it is present here only. Now, what about my T2 and T3 means? T2 is less than G, so that's why it should come to the left child and it should present at this side. And T3, my T3 is always greater than G, it should come to the right child, so it is always less than C, comes to here only. Now here you can see the example. Now this is R, this is C, and this is my G. When I applied R and L rotations, finally my tree structure should be represented like this, right? This is to be called as RL rotation. I hope that you all understood all the 4 rotations. So what are the 4 rotations? We have R rotation, L rotation, LR rotation, and RL rotation. What is the purpose of these rotations? These rotations are used to make the binary search tree into a balanced binary search tree, right? Now here we are going to see how to construct a binary search tree or an AVL tree. Just I'm going to play a small video. See that video, how all the different rotations are implemented. Try to understand it. Listen the video and understand it. Right. I hope that you all understood how different rotations are used in constructing this tree. So here we are going to see an example how to construct an AVL tree by taking some elements. So here we are taking the elements 5, 6, 8, 3, 2, 4, 7. So first I need to insert 5. First element I am taking. So its balancing factor is 0 since that it doesn't have any childs. Next I want to insert 6. Obviously, the 6 is greater than 5. So that's it should be the right child of 5. So I represented it in the right child. And 6 doesn't have any left child and right child. So its balancing factor is 0. And here it is having 0 left childs and 1 right child. So its balancing factor is -1. Right. Now, after that, I need to insert 8. So here I need to insert 8. So obviously we know that 8 is greater than 6. So it should become the right child of 8. Now here the balancing factor. Here left child is 0 left childs and 2 right childs. So the balancing factor becomes -2. But my AVLC should have a balancing factor of either -1, 0 or +1. Either -1 or 0 or +1. So that's why. So I need to apply. So for making it height balanced, I need to apply the rotation. So here the suitable rotation for this is L rotation. So that's why we made it as L rotation, L rotated. Then when I made it as L rotated, 6 becomes my root, 5 becomes child, and 8 becomes right child. Right. Now the balancing factors of all the rows becomes 0. Right. After that, I'm going to insert 3. So I know that 3 is less than 5. So that's why it should be the left child. Now here you can see the balancing factors. Here this is 0. And here this is having 1 and 0 right child. So its balancing factor is 1. Here it is having 2 left childs and 1 right child. So balancing factor is 1. And here also this doesn't have any left and right child. Its balancing factor is 1. So this is height balance. So no need of doing any rotations here. Right. Now after that, I'm going to insert next element 2. Right. I know that 2 is less than 3. So that's why it should be the left child. Now here you can see that now balancing factor is changed here. Right. So it is having 2 left childs, no right childs. It is having 3 left childs, 1 right child. So in both the cases, balancing factor is required. So in this case, I need to apply R rotation. Right. When I applied the R rotation, my tree becomes parent and my 2 becomes child and 5 becomes right child, right? So this is height balanced again. Now I'm going to insert 4. So I know that 4 is less than 6, so it should be the left child, and it is greater than 4, it should be the right child, and it is less than 5, it should be the left child. Now, if I made like this, here you can see I have 3 childs in the left subtree. Maximum depth is 3 childs. But here I have only 1 child. So here 3 minus 1, whose balancing factor is 2. I need to change this balancing factor. So that's why we are applying LR rotation. So by applying that LR rotation, by 5 becomes my root node, and 6, 8 becomes the right child, 3, 2, and 4 becomes the left child. Now it is height balance, right? Now I want to insert 7. Now I know that 7 is greater than 5, so it should be here 6. 7 is greater than 6, it should be the right, but 7 is less than 8, it should be the left. When I place the 7 here the height balancing is missing. So that's why we are applying RL rotation. When I applied RL rotation, my 7 becomes the parent, and my 6 comes here, and 8 comes here. Now the tree is height balanced, right? So this is the process of construction of AVL tree. So I hope that you all understood how to construct a AVL tree using different rotations and making it as height balanced, right? So next we are going to see the example of 2-3 trees. So what is a 2-3 tree? A 2-3 tree is a type of balanced search tree where each internal node can have either 2 or 3 children. 2 or 3 children it may have, right? Now 2 node contains a single key K and has 2 children. Okay, 2 node tree means contains a single key has 2 children. Here single key is present and 1 key is present here, another key is present here. This key, the left key always less than the parent, right key is always greater than the parent. And 3 node tree. So what is 3 node tree means? Contains 2 ordered keys K1 and K2. Always the K1 should be less than K2 and has 3 children. Here this is 1 children. Here this child should be less than K1, and this child should be greater than K2, and this child should present in between K1 and K2. Like that 3 childs should be present, and it accepts the presence of 2 nodes, right? Now here we are going to see construction of 2-3 tree, how to construct a 2-3 tree using successive insertions of the given elements. First I am going to insert 9. Next I am going to insert 5. 5 is less than 9, so I can represent K1, K2, 5, 9. Now insert 8. So since 8 is in between 5 and 9, I can represent it as 5, 8, 9. So how I am making it as height balance? So 8 comes here, 5, 9. So since 3 keys are not accepted, so I am making this as left child and this as right child. And I am going to insert 3. Since 3 is less than 5, it should be present at the left of 5. Now it allows the presence of 2 keys. That's why I represented 3 and 5 in the same node. Now next I need to insert 2. When I inserted 2, here this 2 is less than 3. It should be the left of 3. But here 3 keys are not accepted. So that's why we are splitting it. The 3 comes to the parent and 2 comes here. And here the 5 is present in between 3 and 8. It is the 5 and it is 9. Here this is a 3 node key. 3 node, right? Now I am going to insert 4. When I am taking 4, this is lies between 3 and 8, and it is less than 4. I can write here. Next I am inserting 7. When I inserted 7 here, it is greater than 5. Since 3 keys are not accepted, now here you can see this 5 comes to here, 3, 5, 8, 2, 4, 7, 9. Now when it cannot accept the 3 keys and it cannot accept 4 childs. That's why again I'm transforming it as 5 is the root node, 3 and 8 are the left and right childs. For 3, 2 and 4 are left and right childs, and for 8, 7 and 9 are left and right childs. So this is the construction of 2-3 tree. So I hope that you all understood the balanced search trees, both AVL trees and 2-3 trees. So try to solve by taking a list of elements to construct AVL and 2, 3 trees. So I hope you all understand. Thank you for listening. Thank you.